Okay, so as I said, we only have transformations on the sine x curve and the cos x curve. So we're going to have a look at transformations of the sine x curve first. So the first transformation we're going to take a look at is this one, where the graph gets stretched, if you like. So what I have here is I have the original sine x curve is here, of course, in blue. Okay, so remember the three important points. You have your general shape there. You know that the period is 0 to 360 degrees. It cuts at 0, 180 and 360 degrees. Of course, the same as 2 pi in radians. 180 degrees is the same as pi radians. So that's where it cuts the x-axis. Now, the green graph is y equals 2 sine x. Okay, and the effect that a 2 has, or any number that is in front of the trig graph, the effect that this has is the graph stretches. Okay, so it affects the y-axis. Rather than having a range of -1 to 1, we now have a range of -2 to 2. Okay, so this is what's also called the amplitude, all right? This space between your midline equation, which in this case, of course, is the x-axis. There's my middle line there. Okay, I'll talk a little bit more about midline equations later on, but there's your middle line, right? And then this distance here, between here and here, and obviously here and here, we always take the positive distance. Whatever that distance is what we call the amplitude. So that's what this affects. So it has a stretch effect. It affects, of course, the amplitude is the other key word that I will discuss in more detail as we go on as well. But watch, it does cut the x-axis in the very same way. So the only effect the number before a trig curve has is the effect on the y-axis where it stretches the graph. So this is another transformation on the y equals sine x curve. There's your sine x curve there, the original, of course. That's your general shape. That's the shape that repeats every 360 degrees. It has a range of 1, -1 and cuts 0, 180, 360. And of course the orange graph we can see is cutting in the very same places, has the very same shape. The only difference is this stretch, and this time it's going up to 3 and down to -3. So this graph is the graph of y equals 3 sine x. Remember, the number before just affects this amplitude. Okay, so this distance here between that middle line and your maximum and minimum points. Okay, so it's a stretch, and then the range is affected where it is now -3 to 3 instead of -1 to 1. Okay, so this is another transformation on the sine x curve. There's the sine x curve again in blue, our original, okay? And what we have in red here now is the graph y equals sine 2x, okay? Where the 2 is here by the x, and therefore it's affecting the angle. And the effect that it has on the graph, if you can see here, is the graph, the original graph is squashed, if you like, okay? There's a squashed effect where there's my original blue, okay? So that shape, that original shape that's repeated, there's twice as much of that shape now in that original period. So there's 0 to 360 degrees, where there is usually just this horizontal backwards S. There are now 2 of those horizontal backwards S's, okay? So there's double, if there's a 2 there, there is double the amount of graph in that same space as there originally was, okay? So where it cuts the x-axis is affected. All right. The range, however, is the very same. So there's no effect on the y-axis. We still have a -1 to 1 range. But if we want to know exactly where we're cutting now, well, think of your original. Your original cuts are the cuts, of course, you need to know off very, very well. So 0, 180, and of course 360 degrees. That's the same as 2 pi for 360 degrees, and 180 degrees is equivalent to pi radians. So if I know what my original cuts are, okay, then to find out where the cuts are going to be on the sine 2x curve, all I need to do is divide by 2, divide by 2, divide by 2. And of course it cuts every 180 degrees after. And of course it's going to be the same that if I'm dividing this by 2, divide by 2, divide by 2, because we have twice as much curve now in the original period, then the sine 2x curve is going to cut at 0, 90, 180, and every 90 degrees after that. Okay, so that's a really useful way to know exactly how you can figure out where that new curve cuts. So the original cuts is 0, 180, 360. If it's a sine 2x curve, so there's a squash, there's double the amount of curve in the original period, then we divide these all by 2, and that's how we find the new cuts on the x-axis. Twice as much curve in the original period, but the range is the same. Okay, so here's another transformation of the sine x graph. We can see our original sine x curve in blue, as always. And of course, this time in green, we have the sine wave, the shape once, twice, 3 times within the 0 to 360 degree period, range 1 and minus 1. So this curve is y equals sine 3x. And of course, the effect with the 3 is there's now 3 times as much curve squashed in that original period as there was before. So the original period had this shape just once between 0 and 360 degrees. We now have that shape once, twice, and 3 times. Okay, so where does this cut the x-axis? Well, if we look at our original cuts, our original cuts, of course, is 0, 180, 360, and every 180 degrees after. For these cuts now, to see exactly where these cut, so there's your 180, and there's your 360. In other words, your 2 pi, and your pi, and obviously your 0. So now the y equals sine 3x curve cuts, well, we'll divide that by 3, divide that by 3, divide that by 3, divide that by 3. So we're cutting at 0, 60, 120, and every 60 degrees after. Okay, so that is 0, 60, 120, 180, and so on every 60 degrees. Okay, so it's the sine 3x curve. The 3x, when the 3 is in front of the x, of course, that causes the squash. There's 3 times as much curve squashed into that same period as originally, but the range is still minus 1 to 1. Okay, so let's have a look at some of those basic transformations on the cos x curve. So we can see we have our U shape here, coming from the y-axis, and our cuts at 90 degrees and 270 degrees. In other words, 3 pi over 2 and pi over 2. Okay, so this we can identify immediately as the cos curve. The original is in blue there. And then the transformation in purple, so we can see it is still cutting in the same place, but there's an effect on the y-axis. Our graph is now stretched. And do we remember the stretch effect? So if it's now going from a range of minus 2 to 2, but we're cutting in the very same places on the x-axis, the purple graph is now the transformation y equals 2 cos x. Remember, the number in front causes the stretch. It affects, of course, the amplitude, which is what we have here. And because it's 2, we now have an amplitude of 2, distance of 2 in other words, between the graph and the middle line. Okay, in this case our midline equation is y equals 0, or the x-axis. So the 2 there says tells us the range is going to be -2 to 2. There's just going to be a stretch on that original cos x curve. And now let's take a look at this transformation. So again, from the y-axis, we can see we have the U shape here in blue. This is our original cos x curve. Okay, range of -1 to 1, cutting at 90 degrees and 270 degrees. In other words, 3 pi over 2 and pi over 2. But this time we have an amplitude of 3, okay, from that midline equation. Okay, that middle line y equals 0, in other words, the x-axis. So what we know now then about this graph in green, it must be, of course, y equals, and given the range is now -3 to 3, it must be y equals 3 cos, and still just x because we are cutting, of course, in the very same places as the original cos x curve. Okay, let's take a look at this one. We have, of course, the blue curve there, the U shape, again, coming from the y-axis. -1 to 1 is the range, that's our shape and our period. Cutting, of course, here is 90 degrees, or pi over 2. And this cut here, of course, is 270, or 3 pi over 2. Okay, so that's that cut there and that cut there, the original cos x curve. And now what I have the very same range, -1 to 1 with the red curve, but I have a U here and another U here between my 0 and 360 degree period. There in blue is my original U shape that repeats itself in the period 360 degrees. And now within that very same period, I have 2 U shapes in that distance. So that implies that this is the curve y equals cos 2x. There's twice as much curve squashed in there as there originally is, and it of course affects the cuts on the x-axis. So the original cuts, let's analyze that. Well, the original cuts on the y equals cos x curve are of course 90 degrees, 270 degrees, and every 180 degrees after. And of course now if I have y equals cos 2x, that is going to cut, we'll divide by 2, divide by 2, and divide by 2. It is going to be of course 45 degrees, 135 degrees, and every 90 degrees after that. And they are where the cuts now are. The range, of course, is still -1 to 1, as there's no number in front to affect the amplitude. Okay, so take a look at this one, and there is the original curve there, y equals cos x, and now what is the curve here that is represented by the orange graph? Pause the video and write the answer down if you feel confident. Well, analysing what we have here, we have the same range as the original, -1 to 1. There's our original period, our U shape. We can see that clearly with blue. And of course, the orange, we have now 1, 2, 3 of those original U shapes within that very same period. So it is, of course, y equals cos 3x. And if we're to analyse, of course, the cuts on the x-axis, which aren't clearly written out there, and this is often a question where you have to identify what these points are. So again, all you need to remember are your original cuts with your y equals cos x curve, which of course are 90, 270, and every 180 degrees after. So then for the y equals cos 3x cuts, all you need to do then is divide by 3, divide by 3, divide by 3. So we are talking about 30 degrees, 90 degrees, and every 60 degrees after. Okay, given what you now know about the different transformations, looking at these graphs here, give me the equation of the function that is here in blue and also the function that is here in red. Pause the video and see if you can work that out. So in blue, we have, of course, a range of -1 to 1. We have this nice U shape between 0 and 360 degrees and cuts at 19,270. The blue is obviously the y equals cos x original curve. Now analyzing the red is also a U shape, but there is 2 of those in that original period. Okay, so that means there's a squash effect on it, but there's also a stretch on it as well. Okay, because now the range of the red curve is -3 to 3, we have both a stretch and a squash. So this is going to be, if of course there's the stretch, in other words we're affecting the amplitude, then we know that that is going to have an effect on the number in front, and since it is -3 to 3, the range or the amplitude is a distance of 3, we have 3 in front. It is of course a transformation of the cos curve, and we have a squash. We have 2 of these U shapes now in my original period of 360 degrees, which implies it is y equals 3 cos 2x. There's twice as much curve squashed in as the original into the original period, so that's the effect that that 2 has, and the 3 of course is the amplitude, in other words the stretch, and the range is now -3 to 3, so the effect of that leaves 3 cos and 2x. Let's take a look at this example. Now what we have here is we have this blue shape, okay, is of course our original sine x curve, okay. We have there between 0 and that is of course 360 degrees or 2 pi. It's cutting here at 180 or pi. And of course that original blue is that horizontal backwards S shape, range as I said -1 to 1, so that is y equals sine x. Okay, now what we have in turquoise then is basically that shape, that original shape reflected in the x-axis, and the effect that that has is it is a minus sine x. So whenever you have a minus function, it is a reflection of the original f of x function in the x-axis. Okay, so minus f of x is a reflection of whatever function it was, f of x, in the x-axis. In other words, your x-axis, it acts like your mirror line, and then you just reflect the shape, that original shape, in that line. So anytime you have a minus, the effect it has is it is a reflection of the original in the x-axis. Okay, one final transformation I want to show you before we start mixing some more of these is this one. So taking this curve here, if you've spotted already what it is, we have a range of -1 to 1 of course, and we have a U shape between 0 and 2 pi or 360 degrees. So that is of course the original y equals cos x curve. And then this one in grey is the very same curve and shape and very same size or amplitude if you like, but it's just moved up. Okay, and it has moved up. If you have a look here at the 1 is now up at 4, so the whole thing has been shifted up 3 units. So the grey curve is the function y equals 3 plus cos x. Okay, up to now we've been looking at numbers directly in front of the trig function, or when the number was in front of the x, in other words, affecting the angle. But if the 3 or the number is just being added onto the function, it is just a vertical shift 3 units up. Okay? It also relates to the midline equation. Okay, it gives you an indication of where that is. So I've discussed a little bit about the middle line. Okay, so there's the middle line in the original cos x curve. Okay, and that equation is the equation of the x-axis. And of course, the x-axis has an equation of y equals 0. And the reason, of course, the equation is y equals 0 is because everywhere, every point along that line has the y coordinate equal to 0. For example, that's 0, 0. That's pi over 2, 0, or 90 degrees and 0, if we're in degrees. That point right there is pi 0. Every single point, the x-coordinate is different along this line, depending on where you are in the point, but the y-coordinate is always 0. So this middle line, or the midline equation, is y equals 0. Whereas up here, the middle line of that graph is now here. And of course, it's right here at 3. So this is the line y equals 3. So this number here tells you, of course, what the midline equation is as well. Okay, so it gives you the indication that we have a vertical shift upwards because it's positive by 3 units, and therefore the midline equation is y equals 3. Okay, so here's the important note, all right? Just to sum everything up that we've just been looking at and we've just gotten a nice visual on, okay? We're talking about the transformations on either the sine x curve or the cos x curve, okay? We don't have transformations on the tan x curve. That's not on our curriculum. We don't have to worry about that. So it's either of the form y equals a plus b sine cx or y equals a plus b cos cx. In other words, you could have a number here, you could have a number here, you could have a number here, and each of these numbers has a different effect on the curves, okay? And we've looked at that visually bit by bit by bit there. So what I want to put down now in a nutshell here in this important note is exactly what you can pull out with regards to each of these numbers, or look for in the graph to be able to plug in the values for each of these numbers. So the first one is this, okay? We've talked about the number here just before. This being added on gives you a vertical shift, of course, and it gives you the midline equation. So y equals a is that middle line of the graph and the equation of that line, okay? So that's the first important point about the value that appears here. And of course, if it's 0 or there's no value being added on, then it's y equals 0. The x-axis is the midline equation. This we've already talked about is, of course, it affects the stretch. It stretches the curve, and we talked about it affecting the amplitude, okay? Now, we talked about the amplitude being the distance, remember? And of course, distance is always a positive value. So we look at this value, we take the modulus of this value, in other words, the distance of the value, which just means you always take the positive number to represent the amplitude. And the amplitude, of course, is to do with the stretch. So looking at the top of the curve, the maximum value, and the distance between that and the midline equation, okay? And you're always taking the positive value. Then we have the amplitude, of course, gives you another bit of information about the range, okay? Because the range is basically going to be, depending on the midline equation, of course, it'll be a minus whatever that amplitude value is and a plus whatever that amplitude value is. Okay, now you can see that that looks maybe a little bit more complicated written down like that, but it's a very easy one to spot on the graph, isn't it, what the range actually is. And then the last one here is to do with the period, okay? Okay, so what's useful with this is there are two little equations that can be useful depending on what questions you're asked here. The period is always equal to 2 pi divided by c, or of course 2 pi is the same as 360 degrees. So that C value, whatever that value is, the period is always 2 pi divided by that, okay? Or another way of looking at a rearrangement of this equation is that the C value is equal to 2 pi divided by the period, all right? So remember, the period is that shortest distance along the x-axis, after which the graph will repeat itself, okay? So let's have a look now at some more questions, and we can put all of this into practice. Okay, so take a look at this graph here, and what I want you to do is identify what the equation of this graph is. Okay, so there's lots of things to possibly fill in based on our notes from before. You might have a value for A, B, and C to fill in, depending, of course, if it's the sine curve or the cos curve that we're looking at. So that's the first thing you want to identify for yourself. Pause the video if you feel confident to give this one a go. Otherwise, listen in and we'll go through this one very thoroughly. So the first thing, as I said, to identify is, are we talking about the sine x curve or the cos x curve? Okay, so looking at the shape from the y-axis, we can see it's going up and then down and up and then down. So that is quite clearly the sine x curve, okay? So it's not a U shape coming from the y-axis, it is that horizontal backwards S shape, okay, coming from the y-axis. So straight away, it's the sine x curve. So now it could be a number of transformations of the sine x curve. So we basically have possibly 3 boxes of values to fill in here, okay? So the first one, remember from your notes, is the midline equation. All right, and if we look here where our middle line is in this graph, we can see that we would draw that middle line here, okay? And that would be, of course, at 2. So that's the first value we can fill in there because that is the midline equation, all right? Then we're looking at our amplitude, and our amplitude, remember, is always the distance from that middle line to the highest or lowest point. And of course, the distance there on each side is, of course, 3. So there's our amplitude. We're going to fill that in next. And then we want to see, of course, about the C value. And remember, the C value is 2 pi divided by the period. Or if you want to look at your original 0 to 2 pi, your original period, of course, with the original sine x curve is 2 pi. And how many of our shapes do we have within that original period? We, of course, have 2 of them, which means we've got a squash, twice as much curve in that original period, which means that value is going to be 2. All right, in other words, that C value is 2 pi divided by the period, of course, of this graph. The shortest distance on the x-axis for which this repeats is 90 degrees. So, in other words, 2 pi divided by pi, which of course is 2. It's easiest, of course, to analyze just your original period. Again, always going back to your key points from your original function, and however many shapes appear, original shapes appear within that distance, gives you a clear indication of what that C value is. Okay, here's another function, and pause the video and see if you can write out the full equation of this function for me. So the first thing to identify is whether we're talking about the sine x curve or a transformation of the cos x curve. And again, looking from the y-axis, we're going up and then down and then up and then down, which of course gives us the sine x shape. So we're talking about a transformation of the sine x function. So there's possibly 3 things to fill in here. Let's have a look. That first one, remember, is the midline equation, and the midline equation here happens to be 1. Okay, this of course affects the amplitude, so we're looking at the distance then from that midline equation to the highest points and the lowest points of the curve, and of course that is a distance of 2. All right, and then we are looking at the value for c. So again, as I said, the easiest thing to look at is, of course, your original period. So there's your 2 pi, right? And normally what we have within that period is we would have one sideways horizontal backwards s, for want of a better way to explain it. But this time we have 1, 2, 3 of those. So that means that is going to be sine 3x there. So the function is 1 plus 2 sine 3x. Okay, and our final example. Pause the video and see if you can figure out what the equation of this trig graph is. So like always, the first thing we want to identify is whether we're talking about the sine curve or the cos curve. And looking from the y-axis, we have it going up and then down, and then up and then down. It's not our horizontal backwards S shape quite. It is actually an upside down U shape. Now, if it's an upside down U shape, we've got a transformation, of course, of the cos x curve. And because it's been flipped, and normally a cos x curve is all about the U shape. Because this is an upside down U shape, we are talking about a transformation, in other words, with regards a reflection of the cos x curve. So do we remember that? The minus causes a reflection in the graph. In other words, the graph shape will be flipped, okay? Now, when we looked at it, it was flipped in the x-axis, but obviously the whole graph has been shifted up from the x-axis. So it has been flipped. There is a reflection of the shape. So that's how we know we're definitely dealing with a minus cos x curve. Now we got to figure in the rest of the transformations. So again, the first number here is going to be your midline equation. So the middle line in that graph is going to be here. So again, we're talking about 2. And then the amplitude, okay, so the distance between that middle line and the maximum minimum value is, of course, 1 unit. All right, so instead of course, it being flipped in the x-axis now, it's being flipped in the y equals 2 line. And we have cos, and now we want to analyze the shape. So the original shape, remember, of course, a cos x original shape within 0 and 2 pi is a U shape. The flip of that would be an N shape, I guess, but there would still only be one N shape in that original period, 0 to 2 pi. We can see quite clearly now we have 2 N shapes between 0 and 2 pi there. So that means that is 2. So y equals 2 minus cos 2x is that function.